Okay, and welcome back to another week of 1728. This week we're going to be going over some construction concepts and the framing systems associated with those, so framing out your walls, your floors, and your roof. Hopefully a lot of it is just kind of review from 1708, and I'm sure your instructor for 1708 it went over in much more detail than I'm going to, and probably knew much more, or definitely knows much more than I do. But I do know that some of you guys are dual enrolled in 1708 along with this course, or maybe some of you took 1708 quite a while ago, and so I just kind of want to act as either a refresher for you guys or just kind of a mini condensed course about how the construction systems fit in our buildings. And so the first thing we need to remember is that we can really break our building down into four main construction systems, or four main components. The foundation, which we discussed last class, its purpose is to evenly distribute the load of the building throughout the soil so no damage can take place. We often would damp proof it to keep water damage from happening and seal off the foundation, because especially with the materials we tend to use for foundation, waters can seep through those walls through capillary action. Then sitting on top of our foundation is our floors, which is the surface that we do most of our activities on. Our flooring is laid over our foundation walls, and it can be done with different materials, but we always have to make sure that we give care, especially if we're doing anything on grade, that the ground below is well compacted. The other purpose of the floor, other than to just be able to stand inside the building, is to prevent that dampness from rising and have this surface to just keep nice and hygienic and clean. And we'll look in the next lecture all about, or not all about, but over how flooring systems are created and how they're framed. Then sitting on top of our floors is our walls, which are our vertical members that the roof rests upon. They help us provide privacy as well as closure, and we'll have various openings in those walls for access to the building for people, or for our pets too. Can't forget about those little angels. And as well as openings for ventilation in our walls. So that just kind of means that there's more to openings than just windows and doors. Dryer vents, soffit vents, all of those things, those are openings as well. And then finally we would have our roof system, which is the protection for people in the building. There's lots of different shapes of roofs, but they are really just defined by if they're flat or if they're sloping, and then what degree is it sloping to. Sloping is really preferred to help shed water or different loads that might be going on the roof, such as snow. And even a flat roof itself still tends to have a slow slope towards a drain, just to help keep it from becoming a pool that'll just eventually collapse in. And then overhang on the roof is also a need to help that shedding water go away from the building instead of just dripping down the sides. So in our small building practice, our roof really isn't an ideal roof, because as that water comes down the slope onto that west wall, it would just fall down that side. It's one of the reasons why we have to have that gutter there on the west wall, because otherwise that side of the building would just get completely ruined through water damage. Within all of these systems, we have different materials that we might use, and we would represent those through different hatch patterns, which is just our kind of visual shorthand. But we would probably use abbreviations as well in just notes and liters. The materials that we're gonna select is based on the building code. So what is the minimum requirement that I would have to have for strength and for R values and things like that? What is the function of the or the part of the building. So the materials that I'm going to use for the foundation are typically not going to be the materials that I use for the walls. The framing members that I use for the roof are probably not going to be the same size framing members that I use for the walls. So it's what is that function of where it is, and also where is the building located to would maybe come into play of what materials you would choose. The economic factor of how much is this building or how much is this material going to cost versus how much is our budget. And you also need to take into consideration that initial investment in the material versus any upkeep that may need to be done to it, or how much money it may save on energy bills and things like that. And we'll look at that in just a moment. And then the environment that the material is going to be interacting with. So once again, our foundation, since that's in the ground, is going to have a different material than our roof. And whenever we're showing these materials, we always need to think about its actual dimension versus its nominal dimension, which is what size is it in reality versus what size do we just call it typically just for notes or for purchasing. And then also, what scale is your drawing going to be in? So the smaller the scale we have, the less detail we put into the materials and the hatches and all of the fine notes. And that's because if I'm drawing something smaller, I can't fit in all of those tiny, tiny, tiny details. So what I need to then take into consideration is what size am I at and how much can I put in the drawing before it gets overly complicated. So our environment has impact on our building in kind of two different forms. We have slow impacts, and then we have kind of dynamic ones that kind of happen instantaneously. So we have environmental factors that are slowly weathering away and causing damage to our building from the moment we start construction. We have water causing damage to our building, which is going to just seep into the materials, causing them to deteriorate. It's not going to be an instantaneous thing by any means, and if we seal our building up well, then it won't have a big impact, but it's still going to be kind of affecting our building. We have thermal factors, such as the light coming through and maybe dulling away some of our colors or causing some of our materials to become brittle and then crack, as well as just the insulation in our building to help keep the inside at a conditioned area or space versus the outside. And then we also have the soil that we are building in, which the soil is different everywhere. And so based on the soil of where you're building is going to then have an impact on what type of foundation you're going to use, as well as just the materials that you might use for your foundation. We'll have, things like termites and other bugs too. They're going to, depending on, I guess, how severe it is, it might be a dynamic problem. But they're going to just slowly kind of weather away the building. And then we have dynamic issues such as earthquakes. That is something that is going to impact your building, and it's a kind of immediate problem. Building around Boone or Watauga County, and even most of North Carolina, or I would say personally all of North Carolina, but I don't know, I didn't grow up around here, so maybe I'm mistaken. Planning for kind of earthquakes is not really a major concern, at least definitely around here in Watauga. But if I was building something, in California, that might be a factor that I put in for my foundation, as I use, brace downs to help make sure that my walls are really, really secured to my foundation. And wind as well. especially in the form of like a hurricane. Wind can have a huge impact on our building, and it's just then it's kind of a constant force hitting against the sides of it. Then within our plans too, so in our design and our construction, we have different regulatory influences such as zoning laws. And so I touched on this very, very, very briefly in the site planning lecture, but you'll be zoned for whether or not a building is, or a piece of land is able for commercial or residential, and they are typically separated. We're starting to see a big pattern even in kind of more suburban and rural areas for there to be kind of mixed zonings, but it's really popular in kind of bigger cities, and it makes sense from an environmental standard of putting shops near where people live and putting people's houses near shops, just so that way there's less need for transportation. If I can walk to the store, then chances of me needing to get in the car to go grocery shopping is a lot less, versus here in, Watauga County, especially for where my house is, I can't walk myself down to a store. I really have to get in a car, or I have to get on public transport in order for me to go shopping. And so we're seeing kind of more of a shift towards mixing those areas in to encourage people to use public transport or just to walk to places, which I think is a very good thing. And then we also have building codes for the minimum standards of how you can build, and that's going to vary from town to town, as well as state to state. Most building codes are based off of the International Building Code, or the IBC. Some structures may be grandfathered in, so they don't have to necessarily follow the building codes, but if any new construction was to be done on those buildings, then they would have to adhere to the codes. And so one thing that, for an example, is the Biltmore. A lot of the Biltmore is not built to the modern code, which makes sense because it wasn't built when the building code existed, but they are allowed to keep it that way because it's a historic site, so it's grandfathered into it. And then some influences related to accessibility, which mostly this is going to factor into commercial sites or just kind of public areas, but it comes into play with the Americans with Disabilities Act, which was signed in 1990 to say that everyone has the right to access a building. And so there needs to be slopes within like the sidewalk to make sure that I can get into the building. There needs to be ramps in order for me to access it. Within hallways and within rooms, we should have a minimum amount of turning radius or radii, so that way if I'm in a wheelchair, I can at least turn myself around. It's the same thing too of the, rooms and labels, or labels outside of rooms will have to have Braille on them. And in public buildings, so such all the buildings around ASU, all of these things are met, and there is a person that comes once a year to verify that we're following all of this. So they audit it, and it's a random audit, so we don't know when the person's coming. It's the same thing at the high school too. We don't know when they're coming. They just come. They check that we have everything in place. They check our elevators in working order, to make sure that we are providing access and an equal opportunity for everyone. So the first big environmental factor that's going to affect us is the earth, which is going to be based off of our different types of soil. And so there's lots of different types of soil out there. I'm in no way going to sit here and pretend that I am a soil expert. But we've got, particularly around Boone, there is a kind of a high amount of clay in the soil here, which is a good, fairly stable soil, but it's subject for movement towards the top. You can have sandy soil, you can have peaty soil, you can have loamy soil, you can have lots of different types. And you can have a good idea of what type of soil is around where you're going to build, but you don't know until you start digging. So that's why samples are usually taken. And once you know what type of soil it is, then you can make sure that the foundation will be able to deal with it properly. What else? What else did I want to say here too? Did I put that on the next slide, I want to say? Yes. Maybe it's on the next one about the frost line? I think so. Sorry, I made this presentation about 2 years ago, so I can't remember exactly. But for our other factors, like I said, we have sudden movements within the ground that might cause our foundation to shift, and if our foundation shifts, then our building could get compromised structurally. We have insects that also are going to potentially eat through our materials. So with foundations, we'll see rigid foam a lot as an insulation around them, and bugs love that. Bugs love blue board. They eat through it like crazy. And so making sure that you have a good seal around your building is kind of important, as well as just if you have any wood that may be kind of near the ground, or even structural supports that are kind of dug into the ground, is to make sure that there is some type of coating or shield around them to prevent any insect infestations in those. And then, as well as gas seepage around the ground, and particularly water too, is just to kind of collect it and to vent it with pipes. And such as like with water, we'll have that French drain that we saw in the foundation lecture going around the edge of it to kind of help collect that water and bring it away from our footing and our foundation wall, as opposed to directly on it. And then the other considerations we need to consider with the earth is things like our frost line. And so that frost line is the deepest part down in the ground that the ground will freeze. And so we want to make sure that our footing sits below our frost line. If there's any water tables near our construction, to just make sure that we are outside what's called the zone of saturation. And so that way we're potentially not disturbing that water table and then causing all of the water to just seep into our foundation. Then another big environmental factor, which can be a sudden one to plan for, so it's nothing like the earth, which is just kind of something that's there that we have to deal with. This is something that could happen, which is fire. And fires can often start behind the walls or inside of them. And so that's why we'll often have fire stopping and seals for openings and joints, just to kind of prevent fire from going further in that wall than it needs to. Fire blocking is also another technique that we may use to help prevent fire from spreading, which is just additional horizontal pieces of lumber between studs to help slow down the fire. Whenever we do have those protections in place, the walls will be rated for how many hours that they can stand before they become structurally compromised. So this wall here is rated for 1 hour. So it can stay and be okay for 1 hour of exposure. And it's also, will have different doors also and how they are rated as well. So, for example, since I'm here in the high school, we have lots of metal doors at the end of each hallway, and you know, whenever the fire alarm goes off, the doors automatically close, and they are rated for 2 hours, our doors. And so that means that if there was a fire sitting outside that door, it would take about 2 hours before it would become structurally compromised, and hopefully by then the fire would be under control. But I don't know, I'm certainly not a member of the fire department. Heat then is one of the environmental factors that we focus a lot on in sustainable building, because when it comes to energy usage and energy conservation, it's the easiest one to control. And so we're constantly battling with keeping our conditioned spaces conditioned and keeping that outside air out and our inside air in. And or I guess kind of the main part of the struggle is that usually in the summer we want our houses to be cooler, and in the winter we want our houses to be warmer. And so they're constantly at ends with each other, because in the winter that hot air wants to escape, and in the summer that hot air wants to come in. So having a solid and really tight building envelope is the best solution for just that overall energy use reduction in a building. And you do that with your insulation as well. And you'd pick your insulation based on its R value, which is just its thermal resistance. So how well can it battle that need for equilibrium of that hot air outside wanting to make the inside air the exact same temperature that it is. And so there's lots of different materials that you could choose for insulation. One of the more common ones is just batt insulation, which is that yummy pink cotton candy that you'll see inside the walls. There's also been a big shift towards rigid insulation, or those blue boards, because they have a higher R value. So we can, with a little bit more money up front, because they do cost more than batt insulation, you then can conserve more energy and ultimately save money on your bills in the long run. And so not only are you saving money, but you're also using less energy, which then it comes into play environmentally as well. There's also spray foam insulation, which then would cost the most out of these three options. But it would have the overall highest R value, so it would be the most effective of all of them, because you're getting into every single little nook and cranny, and so therefore it's harder for that air to seep in and kind of change a little bit, versus with your batt insulation you have lots of air pockets. With your rigid insulation you are covering a good amount, but there's still going to be a couple of little gaps for it. So it's ultimately then really kind of playing that line of cost effectiveness of how much money up front versus how much money would we save in the long run. And there's even other insulation insulation types out there that you could use. So there's rock wool, which I believe is just like a byproduct of steel manufacturing, but it can be used for insulation. And then there's also, I've seen too, denim insulation, which is kind of interesting. It doesn't insulate very well at all, but they'll essentially take lots of... Sorry, I was looking up what is rock wool made from. Yeah, it's a slag produced by the steel and copper industry. But yeah, denim insulation, they'll take like really old pieces of denim and they'll shred it up into kind of a nice fluffy substance, and you can use that. It has a horrible R value, but it's still, you know, it's recycled material, so it's effective in that regard. And I'll stop going on about different insulations now. And then wind, so this then comes into play with kind of that heat, because the wind can then help transfer those different temperatures to it. And so that movement of air essentially translates to that thermal movement as well. So in the summer, the air in the house is cooler than the air outside. The hot air seeps in through the roof and it pushes the cool air out through the bottom. In the winter, we have the opposite. We have the cool air enter through the bottom of the house and it then warms up and it pushes hot air out through the top. And so that's what's called the stack effect of just your air kind of being constantly moving, trying to reach its equilibrium. And so the more we can seal that building off, the less we have to worry about that effect. Hopefully I've said that enough. I've probably said it about 1,500 times so far. Then we also have water, which, as I described in parts of our foundation lecture, that is kind of our main nemesis of just destroying our materials and causing all sorts of havoc in our building. Water is the number one thing that we have to be aware of, especially then when it comes into vapor as well, just constantly trying to come into our building, and then once the temperature kind of either increases or cools down, it then will turn into water, which will become just the same problem. And so we have water from just rain runoff, as well as snow that will eventually melt and then kind of try to seep into different areas. And so if we ever have openings, we need to make sure that we have joints between those materials where everything is sealed off. And so there's, in this instance, in this section of a roof, we have flashing going on where all of these different joints are made for this this vent, or this drain. So anytime we have a material shift, we have flashing there just to prevent the water from getting into those tiny cracks and then either freezing in that material or just rotting that material away. And then the last factor that we need to always consider in design is just the people that are inside of it, which I think oftentimes gets a little bit lost when it comes to design. So if I'm in a building, it could be the prettiest building in the entire world, but if it's not comfortable to be in, then it really doesn't matter what it looks like. So if no one thought about how I'm going to get from point A to point B, as far as the traffic patterns go, or if no one thought about just, if I'm sitting in this area, what height should these built-in benches be at for it to be comfortable for me to sit? And there's, in the Building Construction Illustrated book that's up on As You Learn, there's a lot of references based on what these heights should be. There's loads of reference books out there too that just kind of go over the average human standards for different heights and different widths. One good way to also think with design too is to not think necessarily about standards, but to design for extremes. So if you are thinking about something height-wise, and it's something that is still accessible for the extreme small and the extreme tall, well then it'll work for the average as well. And so there's an example always about these airplane cockpits that were designed for the average person, but so few people are exactly at that average. And so then if someone was 6'8", they would get into that plane and they wouldn't be able to pilot it. So you can think of it designing for that average, or you can think of trying to design for extremes. And especially just thinking about those traffic patterns of how I'm supposed to get into the building and from one point to another one. If it's not just clear, then it's not really a good design. And so again, I'll hark back to the high school that I'm currently sitting in, is that we have 3 floors, we have 2 staircases, both staircases are located in the exact same spot, and all of the hallways just abruptly end. And so if I wanted to go to the room that's almost directly above me, I'm at the end of a hallway, If I wanted to go just to the room that's above me, I have to walk all the way down my hallway, go up the stairs, then go all the way back down almost the same hallway. No one really thought about how someone would move around this building, and it's the worst. Well, I guess there are worse things in the world, but it's not a good design. They just thought the gimmick of, hey, it looks like a W, but other than that, the design of it is horrible. So think about that design and how people are going to move around before you make your building. So material. So different materials that we may use. First off is concrete, which you can have cast in place concrete or you could have precast concrete. So concrete consists of a mix of cement powder, gravel, and a sand or an aggregate and some water. The common ratio of those is 1 part cement to 3 parts sand to 6 parts aggregate. And then the water is the variant for the amount of strength. So if you have about 0.4 or 0.5 amount of water is really good for foundations. Too much water is going to mean that you have too much space between those different particles that make up that concrete mix, which will make your cement or your concrete weaker. But this mix amount can vary and cause the concrete to have different properties, whether it be visually or structurally. Precast concrete is often used in scenarios where that concrete is visible, and so it has kind of like an aesthetic purpose for it. You may have walls where it's precast and brought to site and then forklift into place. Your typical construction for concrete is going to be something that is load bearing, and the concrete is going to soak up water that is around it even after it's dried, which will start to kind of weaken the structure. So there's also then that potential for the water freezing and expanding and causing cracks and damage in the concrete. And so rebar is often used to help keep concrete rigid while allowing a small amount of flexibility without compromising the structure. And so you kind of have to be careful and make sure that you're sealing everything right with concrete, because and I'm pretty sure I had said this to you guys before, but as our masonry teacher here at the high school says, is that there's 2 things concrete will always do. It'll dry and it'll crack. And so we want to just kind of make it so those cracks will not be harmful. In addition to concrete, we then have masonry forms, which is just what we have our CMUs, which are concrete masonry units, which are pre-made, and we use mortar to connect them with joints. Mortar is just a mix of cement and sand, and it's not as strong as concrete, but it acts as a very good glue. CMUs are often used in scenarios where a cavity wall is needed, and cavity walls are used a lot in masonry jobs as they provide an empty space between materials where water can drain instead of storing all the water inside, which prevents mold from forming and water from freezing, because as I said, is a typically bad thing. And so here is kind of a 3D section of sorts of a cavity wall. And so we can see that there is an empty space between these bricks and these CMUs. And that's just to allow for, as water seeps into these bricks and goes through, it'll just kind of come out this other side, and then it'll get kind of transferred towards what are called weep holes, and it'll just kind of come out at the very bottom. Another fun factor about the high school is that most of the weep holes in our walls got buried underground. So then the water can't actually drain out, and then it just causes lots of puddles and pools, which isn't great when you're in a computer lab. So please don't bury your weep holes, guys. It's not great. Now, another thing that I want to touch on, which should be something you guys are familiar with, but if not, then here it is as news for you, is pieces of dimensional lumber. So the pieces of wood we use to frame our floors and our walls and our roofs with are listed with what we call nominal sizes, but what they're listed with is not their actual size. So a 2x4 is not actually 2 inches by 4 inches. A 2x4 is actually 1.5 by 3.5 inches. The same thing then with a 2x6. It's actually 1.5 by 5.5 inches. And so that small difference in that actual size accounts for the fact when it's at the mill and the saw is going through it, that there's going to be kind of extra cut off. But it also is the fact that the wood is green, or what we call as green when it goes in through that saw. And so there's still a lot of moisture retained in it. And as the moisture leaves the piece of wood while it's sitting there drying after it got cut, it's going to slowly shrink down as that moisture releases. And so that's then also where that little extra amount comes out of. And so if the number in that nominal amount is 1, it's usually just about 1/4 of an inch smaller. If the number is between 2 and 6, and I suppose 7, but if I'm honest, I've never seen a 2x7. But you know, they maybe exist. I don't exactly go hang out in the Lowe's dimensional lumber section all day, so a 2x7 I guess could exist. I won't argue with you about it. But if it's a number between 2 and 6, then it'll just be 1/2 inch smaller. And then if it's 8 or higher, it's 3/4 of an inch smaller. So a 2x8 is actually 1.5 by 7.25. A 2x10 is 1.5 by 9.25. And if I had, you know, a 6x6 post, it's actually 5.5 by 5.5. And so the size that it's just kind of listed as is not the actual size. And when we get into AutoCAD and then as well as Revit, that actual size is very, very, very important, because we're going to frame everything out full size to the T in those software. And so it's really important to know what the actual size of things are. When we're doing hand drawing, since we're doing it at such a small amount, that 1/2 inch difference with our 2x6 is not really going to be, we're not even able to see a 1/2 inch at a 1/4 inch equals a foot scale. So that difference isn't going to be the end of the world for us, or really negligible for us. And when we get into SketchUp, I really think SketchUp is much more suited as a generalization tool than a nitty-gritty perfect details tool. So we kind of ignore that concept in SketchUp as well. But yes, very important. If you didn't know this, make sure you remember it from now on. And then kind of the one thing that we always need to keep in mind too is that buildings are like a composite of different materials. And so even then when we frame our walls out of dimensional lumber, that isn't the only material that we are using in that wall. And so we have different parts that are connected that help make up just our wall, or just our floor, and just our foundation, and just our roof. And even then, furthermore, we have those 4 systems that connect to each other that create the whole composite of the building. And so even just looking at our foundation, a lot of those materials that we're using in the foundation are engineered materials that act as barriers and perform other functions. A lot of those functions revolve around water. We've got gravel, we've got drains, we've got waterproofing. Then we have our CMUs for our structure. Inside there is poured concrete, and then rebar, and then bricks. We've got these metal ties that then help connect our bricks to the rest of our wall. there's lots and lots of different parts. We've got this little thing, which I forgot what its name is, but it's essentially like a little kind of almost loofah-y looking like just material that runs all the way down here that just helps catch all the grout and mortar that may fall out, so that way it doesn't come down here and cause any issues. But I forgot the exact name of it. It's like a little loofah-y sponge thing for doing brickwork. But that's, I'm going off on a tangent. And you can also have, what I have linked here, if I remember correctly, is you can have your insulation built around your walls, which, oops. Okay, there we go. I thought it was broken. So this is actually what my walls of my house are built out of. And so it's foam insulation boards that just kind of interlock with pieces of Legos, and then you have your concrete poured inside of it. Since I kind of lived on 3 sides, my house is surrounded by the ground, and so it really helps the ground itself just acts as a nice insulator, but then this just kind of helps keep everything nice and regulated. And so this is a pretty nifty foundation kind of material too, because it has that insulation pre-built in on both sides. You just interlock them together, you pour your concrete. It's pretty cool. Just in case you wanted to see another option out there. There's so many options out there. Now for framing walls. So there are different parts of a wall frame, and so I just numbered them here based on the number that this picture had them on here. But we start off with our bottom plate, which gets attached to our floor, which is in the next lecture I go over floors and stuff. And then sitting spaced on our wall, we have our studs, which are typically spaced 16 on center. So that means it's 16 inches from the center of one of these to the center of the next one to the center of the next one, and so on and so on and so on. Unless I was doing advanced framing, which I'll go over towards the end of this presentation, and in that case they may be 24 inches on center. And then at the top we have what's called a double top plate, which we double it up to help kind of tie our corners or to help connect our walls together a little bit easier. Anytime we have openings, they'll have a header at the top, and if it's a window, there'll be a sill plate at the bottom, and then any studs that were kind of cut to be shorter because of these openings are what we refer to as cripple studs. The only thing that isn't labeled in this picture then are what we call our king studs, which sit directly on the outside of our openings, and then our trimmer studs, which help hold up our header. And they also sometimes are called jack studs too. So if I have an opening in my wall, I need to figure out where it's going to be located first of all, and then I need to figure out what its rough opening is, which we can find based on the manufacturer's specifications. So the size of the rough opening, or the opening in the framing, would be listed on the door and windows specifications provided by the manufacturer, and then the architect would also include a door and window schedule that would list all of the doors and windows in the house, usually with the nominal dimensions. They would also be identified on the floor plan by a mark of either a letter or a number. All doors and windows of a certain size type would have this same mark. And so if we switch my camera over here to, let me just move it to where I can see it to make sure that we're looking at the right thing. Is here I've got some plans for a house, and I'll zoom it in a little bit. Whoop. And so we can see that all of the windows have this little hexagon marker and some of them have the exact same letter in them. So this is window type A, this is window type A, this is C, and this is C. We've got E, 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 so on and so forth. That just means that this window here is window type G, so is this one. Rather than putting it in the schedule or the little chart that tells me are my window types and stuff, twice, we're just going to say, hey, these windows, they're both the exact same window, spec-wise. Same thing over here. Our doors are labeled with numbers. And so this is door 101, 104, 112, 106, 110, 102, so on and so on and so on. There's no rule that says that they have to get numbered in any specific order. So like there doesn't really necessarily have to be any sense to why is this 104, 105, 106, 107, 108. What it looks like in these plans they decided to do too, so if we go to the lower level, is they started their system with, they put this 0 in the front, which essentially means that this is a door associated with the lower level, then this is on the upper level, and then if there was a floor even higher than that, there would probably then be, you know, 201, 202, and so on and so on. But the hexagon marker says that it's a window, versus the circle marker says that it is a door. And then, if we go here to this sheet that has a schedule on it, let me find the schedule for the windows as well. There it is. So then we have just these little charts, and there are different ways you can do schedules, and I'm like 99% sure I have listed on our class schedule, different type of schedule, that I put schedules on there, which I have written in a little note that it's going to be April 12th. We're going to go over schedules in Revit, because a lot of it can be done automatically for us in there. But this little table here is telling me that door 001, that's its overall size, so it's 2 foot 8 inches wide, 6 foot 8 inches tall. The door thickness is 1 3/8. It's made out of wood. It's wall type C, which that I don't necessarily know exactly what that part means. The frame is also made out of wood, and it's type A. If it has glass on it, it would have it there. And then just kind of maybe what type of lock is on there, and any other little comments that might be included. And the same thing then with our windows, is it tells us the general size of it. So it's saying that all the windows labeled with type A have a 3 foot by 3 foot. The type of window that it might be, any type of glass that it might have, and then any comments. So for instance, this one that's window type H is actually sliding glass doors. And so it's kind of then highlighting that that one is also just these sets of doors, just as a little heads up. And so you can always find then that schedule. It may be located on a different set of sheets or not, but we can always find it. And then for further clarification, because I just found what the types A and B meant, so we have here our door types, and so it's pretty much saying that if it's door type A, so if the door type is labeled as type A, then that means it's going to have this little extra kind of little side part to it. If the door type is labeled as type B, then it's going to be just a plain wooden flush door, but it's going to be insulated. And if it's door type C, which a lot of them are, then it's just kind of a plain regular type door. And this would then be our like accordion folding door. Door type D is also looking like another type accordion folding, but even then I can say, okay, door 103 is a door type D, and I can even just go and check and find door 103, 101, 102, where are you, 103? If I can't find it right away, I'm not going to sit and hold on to it for too long, because I don't want to spend too much time doing that. But I don't see it. I don't see it. I see 104. I see 102. I see 101. I don't see 103. But I'm not going to sit and... Okay, how many times am I going to say I'm not going to sit and stare at it when I'm just going to give up and not stare at it? But my bet is going to be that it's going to be one of these types of kind of bifold doors. Or even a pocket door, it could be. And so that's just kind of how you would find, whoops, my wire is stuck. The different sizes for your openings, you'd frame them for the rough opening. And then, just display. And then you would be able to put your window inside of it. Anytime you have your opening, it's always going to have a header on top of it, which your header is just going to be your pieces of framing material, but instead of going vertically up, they're going horizontally across. And oftentimes there's like a piece of spacer in between to help make sure that it can go across the full edge of the stud. And that's just because we are compromising like the structure of the building by cutting those studs away. Now this weight is kind of compromised in this area, and so by putting the header there, it just kind of gives extra added support. And if I had a window, I would be putting a sill on it, but if there is no window, then there is no need for a sill plate. Because for doors, we would just leave that open to the bottom plate. And sitting on these sides, like I had mentioned, are our jack stud or our trimmer stud, which is just going to be supporting that header, and then our king stud, which would be on either side. Now, the most common type of framing that you will see is called platform framing. And what platform framing is, it's also known as Western framing. And it's used in the houses that have been built in kind of the past 70 years. We call it that because the framing of the floor is built as each level, and it forms a platform in which your work can kind of be done on. A big characteristic of platform framing is that all of the wall studs, which are, as we mentioned, are the main framing members of the walls, extend only the height of 1 story. And the interior walls, which we sometimes call partitions, follow that same rule as well. So the bottom of the studs are still held in position by the bottom plate, sometimes also known as the sole plate. And the top of the studs are held in position by a top plate, which is usually a double top plate, which overlaps at the corners of the intersecting walls to kind of help tie them together. In some construction, that second top plate is not used, and instead metal framing clips are used to tie intersecting walls together. Upper floors rest on top of the top plate of the walls beneath, and the framing members of the upper floors or roof are positioned over these studs of the walls that support them. Platform framing is really easy to notice and see in a wall section, because you can see that these studs extend only from one floor to the next one. Now, another type of framing that exists is called balloon framing. And in balloon framing, the exterior wall studs are continuous from the foundation to the top of the walls. So floor framing at intermediate levels is supported by what we call let-in ribbons. And so the main difference, as hopefully you can see, is that this wall stud goes all the way up, and that our floor joists are kind of just nailed in to our studs rather than our studs sitting on, or our wall stud sitting on top of our floor. But those let-in ribbons is a board that supports each floor joist, and although it's not widely used anymore, some balloon framing techniques are used in special situations. Balloon framing can also be beneficial if you're in an area that has high wind loads because it can withstand more wind, and there's less settling for the building for shrinkage as well. So there are still some scenarios where balloon framing may be kind of more heavily used than platform framing. We're going to focus a lot on platform framing in all of the construction concepts that we do in our drawings for this class. Now, a lot of times we'll have what's called racking, which is just the tendency of all of the studs to want to move over or collapse kind of into this parallelogram shape. And this can be taken care of using diagonal braces, as well as your plywood sheathing at the corners of the building can help prevent this movement as well. But you can use different pieces of braces just to kind of help hold everything in place. Why won't my mouse move? Another kind of construction that it's used especially in kind of mountainous areas around here is post and beam framing. So platform framing and balloon framing, they're characterized by those closely spaced lightweight framing materials. Post and beam framing uses heavier framing members that are spaced further apart from each other, and these heavy pieces of lumber are joined and fastened with special hardware. Now, because this uses fewer pieces of material, it can be faster to kind of erect the building, and although the framing members are large, their wider spacing results in a saving of material overall. The other thing to consider is to span that wider spacing, the floor and roof decking has to be kind of heavier. And a lot of times when you have post and beam framing, it's left exposed to create this special architectural effects. And it can be done in combination with regular wood framing or stick framing, as it's sometimes referred to. And it may just be areas of the house that are done with post and beam framing. Metal framing or light gauge metal is used extensively in commercial construction and places where the strength of structural steel or reinforced concrete is not required. So metal framing can also be really popular in home building where termites and water damage are known to be big problems and issues in that area. So light gauge steel framing uses studs and joists just the same way that wood framing uses, but unlike wood framing, steel framing uses tracks and runners in place at the bottom plates and top plates. So the lighter, less expensive metal frames are not as strong as wood, so they're used a lot for interior partitions, or at least in conjunction with other structural materials. The other kind of, or one of the, I guess, benefits of metal framing compared to wood is that it can be pre-assembled, so just where you have your runner fastened to the floor, and you can put your metal studs in a lot faster, and you have these little openings in your studs to just kind of help run wiring a lot faster. Now, advanced framing is the name given by the APA. It used to be called Optimum Value Engineering, or OVE, but now we just call it advanced framing. It uses 2x6s, which remember are 1.5 by 5.5, and they're spaced 24 inches on center, as opposed to the traditional method of spacing 16 inches on center. Advanced framing also uses aligned framing members to provide greater strength, so all of our studs would be aligned with each other as we're going. So that way that some of those additional framing members can be eliminated and we can have that bigger spacing. When our roof trusses or rafters are aligned directly over the studs, it's not even necessary to have that double top plate. And so we can use less material but still get structural integrity. So if we think about it, when we have our wall framed with 2x4s spaced 16 inches on center, of your entire wall, about like 10% of it is going to be made out of just that wood frame, which isn't really an ideal insulator, and then you have to even have more cuts between your insulation, which just leaves the potential for more air gaps. By using 2x6s and spacing them 24 inches on center, now you only have about 6% of your structure being wood, but you still have that same amount of framing material and your structural integrity is the same. So not only does it reduce the amount of wood exposed to the surface of the wall, but it allows for more insulation inside of the wall, which is just going to then help reduce operation costs altogether. So another thing that advanced framing does well is it reduces the need for wood in quarter construction. So typically when we'd have corners, we would need to use three pieces, to frame the corner of a wall. And there are different techniques to do it, but no matter what, I'm using 3 pieces of wood. And ultimately then I can't get insulation in there, or I can't get insulation behind there. So I'm then just kind of leaving parts exposed. To reduce that heat loss for a advanced framing, only 2 pieces are used, and a metal clip is used to connect the pieces of drywall together to reduce the need for wood, and now I can fit insulation all the way into every little nook and cranny in here. Another material that you may see used are what we call SIPs, or structural integrated panels, which are factory built panels with an insulating core, and then we have OSB, or oriented strand board, adhered to the exterior surface, and even then sometimes on the interior we'll have gypsum wallboard. So both of those surfaces, though, they can be altered to suit the design of the building, so it can be something else. It could be plywood on both sides like this picture shows. And then wiring and piping can also be embedded into that foam core as the panel gets manufactured. And so SIPs are custom designed for every particular application that they're being used for. They get joined together with screws and glue to create this weather type, really well insulated wall, roof, or floor. And the advantage is that they do not include the number of interior framing members that frame construction does. So they do a better job of thermal insulation, and they have a more weather-tight building envelope. And there's also really no waste created at the job site, and the construction is faster. We don't see them used very heavily in commercial construction, but especially buildings that tend to have kind of a more stucco or concrete based exterior, a lot of times are done using SIPs. So when you are laying out your walls and you're thinking about framing your walls, the thing that you always have to consider is that the measurements given on a floor plan are typically going to be given from the face of the frame to either the edge of a wall or to the center of a wall. And it's usually going to be pretty given whether or not they're doing from center to faces. But those exterior dimensions are going from the face of the frame, not necessarily then with the plywood and then other exterior material on top of it. So that's the first thing that always needs to get considered. And before you start framing, it's always a good idea to look at the plan itself and visualize what the layout would be. So if we were looking at this floor plan again, and let me get back over there. So if I'm looking at this floor plan, I need to start thinking about where these measurements are coming from. And so it's going from the outside of the wall to the outside of the wall, but that's to the outside of the frame, not necessarily with the materials added in, which as the builder, that's a good thing, because then I don't have to think about doing the math of subtracting the sheathing and whatever exterior siding is on here. I can just think about, okay, I need to frame this wall out to be 28 feet and 3 inches. You also want to try to think about then where the openings may be located, which unfortunately here there is no opening center, which that's bugging me now that I'm looking at it. I didn't make these plans, but even then I probably would have made way more mistakes than they did. But we still then have from the outside of the wall to then the outside of where this one is. So rather than, what I would typically do is I would typically have these measurements from the outside of this wall to the center of this one, to the center of this one, to the center of this one. What they have instead is from the outside of the wall to the edge of the wall to the edge of the wall. And I can see that these walls here, they're framed out with 2x4s because they're saying that the wall is 3.5 inches wide. So in fact, in these plans, they didn't even specify gypsum wallboard on either side or any of the framing materials. They've only laid everything out based on just the framing structure. And so this wall is actually, or this room is going to be one like square inch smaller based on the gypsum wallboard, but it's really not going to have too great of an effect. You also want to think about walls that are going to have different pieces of plumbing inside of them, and then how that's going to come into the layout. So for instance, we have we've got all of our kitchen stuff right here, which means that if my sink's here, I'm going to have plumbing running in through this wall. I'm going to have plumbing coming in through this one as well, and this one, and here, because if this is where my toilet and my shower and everything's going to go, I need to think about which walls are going to have the different pieces of plumbing going on in them. If I have other features, such as like my fireplace area, so if I've got a fireplace going on here on this lower level, which is this on screen? Yes, it is. Good. This is all masonry work. So I need to think about then how am I going to tie this wall here into it. And the same thing here is if I've got my shower and I've got my sink and toilet, I'm going to have plumbing running in through this wall. You'll also have, which I don't believe is included in this set, but we'll have electrical plans, which yes, I don't have electrical plans for this set. That will then show where the different switches and the different pieces of lighting are, so that way you can also kind of come into play for that. So you always want to kind of think about just the overall layout and where some of those partitions would go. So if I walk into here, I'm going to be met with this slanted wall, and then I have the option to either walk in this way or this way. And then I kind of go up just a few steps, and then, so this is just kind of a little recessed area. I can go up a few steps and then up a couple more. And so it's kind of thinking about how exactly are you walking from one point to another one. And then you can start to think of what these different partitions are going to be, what their overall lengths are going to be, and all that fun stuff. And I knew I was going to keep today's kind of short. And so, like I said, yeah, woo, shorter than I even thought. And so that is just kind of laying out your wall frames. You just need to think about if it's going to be platform frame or not, which most of the time it would be platform frame. And yeah, I don't want to ramble on too much more. So thanks for watching. Make sure you fill out your guided notes, and I'll see you guys in the next one.